Hello everyone, I'm Nguyen from JAIST. I'm here to share with you our work, which is window filtering based noise suppression on task 1 of the Clarity Enhancement Challenge, or CEC3. So, understanding speech in the presence of noise is very difficult, especially for hearing impaired listeners. So, this challenge aims to investigate an enhancement system to improve the clarity of noisy reverberant speech. And this challenge contains 3 tasks. The first is to each task will simulate the room scenarios as much as possible, where task 1 tries to simulate the real room, task 2 is the real recording device, and task 3 is the real background. And our work only deal with task 1. So this is the schematic diagram of the challenge. We will construct the speech enhancement system to process the speech in noise given the audiogram of the listener, and the enhanced speech will be evaluated by the objective evaluation, which is HASP, and the listening test for the intelligibility score, which is the subjective evaluation. So the CEC3 dataset contains the clean speech of 6,000 clips recorded from 39 target speakers, the interferer dataset, which can contain music, noise, or even speech, and the room simulation, which is the procedure to simulate the real scenario, and the observed signal are synthesized, which is binaural, and it can be extremely noisy. So, for example, this is the observed signal.
Nuclear weapons by 2 or more opposing sides would cause the complete annihilation of both the attacker and the defender. Concentrating.
And this is the reference or the target signal.
The one I can't wait for is the European Cup.
Yes, so you can see that it's very difficult to tell the reference signal from the observed one. So our objective in this work is that we will apply the noise suppression method which we previously proposed to the first task of the CEC3, and then we try to extend it to deal with the room reverberation, because in our previous work we only deal with the additive noise. So we hope to contribute some insight on the application of noise suppression method in the context of hearing aid. So in our system, we will apply monaural noise suppression separately on each channel, and then we use the amplifier with the NALR provided by the baseline to amplify for specific listener audiogram, and from that we can have the binaural enhanced signal. So our system based on the mathematical assumption of the noisy reference speech, where the observed signal is obtained by convoluting the anechoic speech signal with the room impulse response and then adding with additive noise. So the question is, how can we apply the additive noise suppression on this kind of observed signal? So we use the approach that is to decompose the room impulse response into the early reflection and the late reverberation. So previous studies show that actually the early reflection does not degrade the speech intelligibility, and only the late reverberation does. So if we decompose this, then after decomposing, the observed signal can have a form of adding the desired signal with the distorting signal. So then this becomes the additive noise suppression problem. So as the problem becomes additive noise suppression, we applied our system to suppress the noise. Our system is based on the Wiener filters, so it will estimate the two parameters. The first is the design variance, sigma x square hat, and the second is the distorting variance, which is sigma d hat square. And if after we have the two parameters, we can construct the Wiener filter, which is the like a binary masking, where the values is from 0 to 1, and we also add one parameter gamma to control the amount of suppression. And to optimize these two parameters, we will use the neural network, which try to optimize the loss function of Itakura Saito diversion, so as this equation. So to train our noise suppression system, we will use the dataset from the Deep Noise Suppression Challenge 2022. With for specific, we will use the rich speech set from of clean speech, which contain only English utterance, and this set have very balanced in the phonemes and have diverse speaker. And we also use the noise dataset with a 62,000 clips of non-speech audio event, and we use the room impulse response, which contain more than 60,000 clips of synthetic IRs and 248 the real room impulse response. And we resample everything from 48 kHz to 44.1 kHz to satisfy the CEC3 condition. So from the clean speech, the noise, and the IR, we randomly simulate the noisy reverberant speech on the fly during training. And actually, there is a reason why we don't use the training data provided by the CEC3. There are mainly three reasons. The first is that the CEC3 has quite a complicated room simulation, so we don't have the explicit IR to extract the late reverberation part. And the second is that the interferer signal can be speech, so it may confuse the enhancement model. And the third is that the pre-simulated signals are actually insufficient for training, so the CEC3 contain like 6,000 scenes, and yes, this is not enough, and we already verified this point in our preliminary experiment. So in our implementation, with the sampling rate of 44.1 kHz, we will use the short-time Fourier transform with 20 millisecond windows, and where the frame shift is less than 5 milliseconds, and therefore the number of Fourier transform points is 1024. Also, the architecture of the design variance and the distorting variance estimators will follow the WaveNet architecture. This architecture have been known to work pretty well on the audio and spectrogram data. So for decomposing the IR, we use the Schroeder integration, which is the ratio between the power of the room impulse response from the time t over the power of the whole room impulse response. And then we can find the smallest t0 such that E of t0 is less than a threshold theta. And then the late reverberation impulse response is the impulse response after t0, and the early reflection is the impulse before t0. So after trying different thresholds and checking the desired signal, we empirically select theta is equal to minus 35 decibel. So actually the observed signals in the CEC3 is extremely tough to enhance because it have a very low signal to noise ratio, and the interferer signals may include speech. Clean speech is not bubble noise, So it's very hard to accurately estimate the two variants of the Wiener filter. And while the original Wiener filter used gamma equal to 1, and we tried this, and actually it used a lot of distortion. So we adjust gamma to 0.01 in the Wiener filter. Yes, and this table shows the evaluation result of the speech enhanced by our system on the development set of the CEC3. So these results show that for all SNR range of the development set, the average hash speed is slightly improved compared to before processing. So here we also provide some demonstration of enhanced speech as different signal to noise ratio. This is the first case where the SNR is less than minus 12 decibel. This is the noisy speech.
Nuclear weapons by two or more opposing sides would cause the complete annihilation of both the attacker and the defender. Concentrating.
This is the enhanced
Nuclear
speech.
weapons by two or more opposing sides would cause the complete annihilation of both the attacker and the defender. Concentrating.
I will not play the enhanced and amplification because the amplification makes the audio very loud. And this is the reference.
The one I can't wait for is the European Cup.
Yes, so you can hear that the actually the target is only appear at the end of the noisy utterance, and in this case the SNR is very low, and the interferer is the speech, so it's actually tell which one is the target. So the enhanced results are not good, and as you can see the hash speed is very low. And in the second case the SNR is minus 1.6. This is the noisy speech.
An uncle had been Lord Mayor of York.
This is the noise suppressed speech.
An uncle had been Lord Mayor of York.
This is the reference.
An uncle had been Lord Mayor of York.
So as we can hear that the noise suppressed speech, in the noise suppressed speech, the noise is actually suppressed quite, and there is some improvement in the enhanced speech. We can see by the hash speed, but this is may not well compatible with the amplification, because after amplification, the hash speed reduced. And this is the third case where the SNR is around 6. This is the noisy one.
Calls to emergency services are not
Each has a telephone and a
no
balcony.
components in place.
And this is the noise suppressed speech.
Calls to emergency services are not
Each has a telephone and a
no
balcony.
components in place.
Yes, actually not much change. And this is the reference.
Each has a telephone and a balcony.
So actually, although the suppression doesn't do much, and but we can still see some improvement in the hash speed. So this is the summary of our work. So in general, very low SNR is still a challenging issue in the noise suppression. Not only for hearing aid, but also for the normal noise suppression system. And also not only realistic scenario simulation, the diversity of the training data is also necessary to train the noise suppression model. And as a result, we only use the DNS 2022 dataset and did not use the CEC dataset. But we can still have improvement instead of using the CEC dataset. And for some point that maybe as future work, that so we may apply the CEC3 scene simulation on the diverse dataset to obtain the realistic and diverse training data, and then we may change the network architecture with the better one, so to have better result, we may consider compatibility between the noise suppressor and the amplifier, because currently we do it independently, and some other technical aspect like phase modification or binaural and multi-channel processing may be taken into consideration.